Okay, let's get started. So remember that whenever you have web work due, a quiz is possible. We haven't had one in a while. I'm not gonna have one today. We'll talk about the lowest success here. But anytime web work is due, a quiz is possible that day that it's due. Okay, but let's go to number 3. So this is this function f, and we have all these integrals that are related to f, and they're integrals of f. So in our perspective of rate of change and amounts of quantities, what would the function f represent? What kind of function would f be if we're looking at these integrals in the light of, or the perspective of rate of change and amount? F would be what kind of function? If it's down, we're taking integrals of f or expressions related to f, then f would be rate of change, right? Rate of change. F would be a rate of change function. So that can help us. So now when we take the perspective of area, keeping in mind that f was a rate of change function and integrals would calculate what? What would integrals calculate? Total amount of change. Total amount of change. We can keep that in mind, and that can help us kind of navigate this area perspective, the area perspective. So if we go from 0 to 2, if we integrate from 0 to 2, this first one, what kind of answer are we expecting to get? We're going to expect to get the integral will be negative. Area is always positive. Area is always positive. So there is a positive area there. But because it's defined by function values that are negative, the integral will be negative. The value of the integral will be negative. Okay? So you could say the value of the integral is like the opposite of that area. The opposite of that area. Okay? And so 0 to 2 would be, so what is that area? That area is 1/2 of a circle, so 1/2 of pi r squared. And what is the radius? 1. So that area right there is pi over 2. So the integral from 0 to 2 of f will be not pi over 2, but negative pi over 2. But then in the problem, there's also a 4. We know that we could just pull that 4 out, right? 4, so constant multiples in derivatives and integrals, they just come along for the ride, right? So you can just factor them out and do them later, okay? Constant multiples like this, like a 4 multiplied, when you do antiderivative and derivative, they just hang around. They just stay around, so we can just factor that out. So the integral from 0 to 2 of f would be the opposite of that area, because f is negative there, so it would be the opposite of pi over 2, and then we're going to multiply by 4. Agree with that? Okay, next one. 0 to 6. So 0 to 6 would be all the way to here. So we're gonna integrate all the way to there. We know that an area perspective is going to have something to do with these areas here. And if we think back to our rate of change perspective, if this is a function f, it's our rate of change function, then what's going to happen to the quantity as x goes from 0 to 2? The total amount of the quantity will change how? As x is moving from 0 to 2, the change in the quantity will be negative. It will go down. The amount of the quantity will go down. The change will be negative, and then when we hit 2 and go to 6, the amount of the quantity will start going up again. So we're going to have a total change that had some decrease and then some increase in the quantity, a greater increase. And so then how can we relate this in areas? If we integrate from 0 to 6 in terms of areas, how would that relate to, say, this is area 2 and this is area 1? Areas are always positive, but what will that integral give us from 0 to 6 in terms of those areas 1 and 2? A2 plus A1. No, A2 minus A1, right? That integral from 0 to 6 will calculate A2 minus A1. That's what we were saying earlier, that when you integrate from 0 to 2, you get the opposite of that area. You get the negative 1 times that area. So if you went from 0 to 6, you'd get that area 2 minus area 1. And then this one's going to be times 5. Okay? So area 2 is 1/2 pi times 2 squared. Area 1 is 1/2 pi 1 squared. And then that whole thing times 5. Questions on B? So that would be the answer for B. So half of the area with radius 2, half of the area with circle radius 1, and then the whole thing times 5. That would be answer to B. So what if I wanted to calculate A1 plus A2 using integral? Now I truly want A1 plus A2. How can I frame an integral expression that will calculate for me the total area, truly A1 plus A2? So there's two ways to do it. The first way is, we know that the integral from 0 to 6, it takes the positive contribution from this area but subtracts off this. So I want to add on that. So what can I do? Yeah, so how do I make it positive? I take the opposite. I'll take the opposite of the integral from 0 to 2. And then plus the integral from 2 to 6. So do you see that that will truly calculate the sum, the total area? That expression right there. Because the area A1 would be the opposite of the integral. Because the integral gives us a negative value. So take the opposite, that would give us A1. And then A2 is just simply, since the curve is in the positive territory there, just from 2 to 6. So that would calculate, that's one way to do it. What's another way to do it? Another way to do it would be to integrate this function. So I'm going to take so if I integrated this function from 0 to 6, do you see that that would truly give me the area of A1 plus A2? So what I'm drawing in blue here. So if I integrated that function, the one I drew in blue, that would also give me the area of A1 plus A2. What is that function in blue? What function is that? What function is the blue function? Do you know? Yeah. Yeah, so if I took the absolute value of the f function, that would make it would make the whole function positive. It's not finding the integral and then taking the absolute value of that. That's not right. It's taking the absolute value of the function, the red function, which gives me the blue function. And then if I integrate that from 0 to 6, it will give me the value that's equivalent to adding A1 plus A2. Do you see it? So two ways to actually get the total area there. Or to express it, I should say. To express it. If we really wanted to find it, we want to break it up into two like this. Because in terms of evaluating that integral, we have to break it up, right? So we're forced, in evaluation, we're forced to do that. But that's another way to express the total area. Okay, questions on this problem? Let's just look at the next one, I think. Okay, so here was the next one that gave a little difficulty. Let's talk about this. So we want to label these from least to greatest. Is that what it says? Least to greatest. Okay? So 0 to 8. 0 to 3. Here's 3. 5 to 8. And 0 to 5. Okay, so let's see here. 0 to 3, 0 to 8. Oh, so this, okay, this is really tricky here. So let's try to find what's going to be the least one. The least one is going to have, it's going to give us the most area below, the most net area below the axis. Which one of those is going to give us the most area below the axis?
0 to 5.
Certainly 0 to 5. 0 to 5 is all of the curve that's negative. So it's going to give you the opposite of all of this area. That would be the least. So D comes first. Make sense? So going from 0 to 5 is going to give us all of that area. Taking the opposite of it will give us the lowest value. Okay? What will be the greatest? 5 to 8 is all positive values of the function. So that will be the greatest area because it will be positive. So it looks like C will be the greatest. So now we just got to figure out which of A and B is greater. 0 to 8 or 0 to 3? 0 to 8 or 0 to 3? Which one's less or which one's greater? So 0 to 3 would be the opposite of all this area. All right, 0 to 8 would have this much more negative contribution, but then it would have all this positive contribution here. So the question is, which one's greater? What is more area, the blue or the red? What's more area, the blue or the red? I guess all we have to go on is to eyeball it, or kind of estimate with these squares, right? So maybe if this is almost a triangle like this, so we could do 1/2, 2 times 1, 2, 3, 1/2, 2 times 4 as an approximation for that. Is that 4? So I think that's about 4 square units, that red. And what about the blue? So, wow, okay. Maybe something like, so I'm going to try another triangle like this. And so 1, 2, so 3, base of 3, height of 2. 1/2, 2 times 3. So I kind of turned those into triangles, just like estimated those with triangles. And I get about 3 square units for the blue and 4 square units for the red. So the red is a larger negative contribution than the blue. So the next least would be to go all the way to 8 or to go just to 3? All the way to 8. Because when you go all the way to 8, so you have this negative, we know this is all going to be a negative value to integral. Then we're going to have an additional -4 plus 3, which nets -1. So to me, it looks like going from 0 to 8 is the next least. And then going from 0 to 3 would be a little bit greater than that. About 1 square unit greater than that. These are all less than 0. And this one is greater than 0. Okay. So did you see what I did there in terms of the reasoning that I used? I kind of estimated with triangles, and then I reasoned about net area, or the difference of areas to get this thing. I think it's DABC. And I want to know for sure. Incorrect. I disagree. So are they saying it's DBAC? If it is, what's that? Then my reasoning was not correct somehow. So what did I do wrong? So I guess my triangles weren't accurate. 1/2. 1, 2, 3, 4. 1, 2, 3. I disagree. But that's why you have 5 attempts. Because it had to be one of those two. But can anyone comment on why you think my reasoning was wrong? I liked my reasoning. Yeah. I'm making that triangle that's the base of 3 and a height of 2. Right? So 3 wide and 2 high, but I'm like estimating with a triangle. And then I'm estimating it with a triangle here, 2 by 1, 2, 3, 4, so 1/2, 2 times 4. I like my solution better. So if you want to keep talking about it, we can talk about it outside of class. Any comments? You guys have any comments about why? Did you like what I did? Yeah, what do you think?
If your red is more negative than the blue, if you're going from 0 to A, you're adding more negative.
Right.
Therefore, A would come.
That's what I said. So that's what I put in first, and it told me I was wrong. So DABC, right?
Oh, no, I mean 0, yeah, B would come first because it's less negative.
But if we're going from least to greatest, we want the most negative to the most positive. So I'm arguing that the most negative would be A, and that's a lower value. You see? Yeah. What's it? But that's what I'm saying. So it would have to be DABC or DBAC, one of those two, and you got 5 attempts. So you can get it right by switching. So I'm not sure what they're after here. So okay. Okay, so remember, so we talked about that. So we're saying that we're looking at integrals as difference of areas. And I think we left off here. So now we want to talk about areas between curves. Areas between curves. And we're going to use the same kind of approach where we're going to think about we're going to design our region or sketch our region, and then we want a typical strip. Typical strip. So the first thing is we need to know how to sketch easy curves. So 1/2 x cubed. Hopefully you can just sketch x cubed without graphing it with technology. We want 1/2 of that, 1/2 x cubed. So x cubed has this, looks like this. So 1/2 is going to also, all the y values would be 1/2. So it'd be like smushed vertically. Okay, so there's y equals 1/2 x cubed, something like that. And x plus y equals 6. Again, hopefully that's something you should be able to sketch. You have some quick method to make a quick sketch of that without technology. So you can think of that as y equals 6 minus x. And lines are straight. Let me try that again. There we go. Okay. So this is our x plus y equals 6. And you have to really read carefully what region. So this is just forms 2 regions. Okay. So don't make the picture and then just assume, like, don't let your eyes just gravitate towards something and you think that's what the region is. You have to read really carefully. That's a big mistake students make, is they don't read carefully enough and they assume a certain axis is part of the boundary when it's not. So we want the 2 curves that I've drawn and the y-axis. So can you see which region that is? The 2 curves and the y-axis. Is it exhibit A or exhibit B? Okay. Okay, you should see with the y-axis, you should see it's this one here. Okay, so we've got our region, and we want to determine that area. So again, we want to look at the area of a typical strip. So we can think about, so what does that look like? So we're thinking about rectangles, but narrow rectangles, skinny rectangles, okay? So like this. So that's our typical strip, and we're going to find the area of that. And it should not. Stops at the curve, right? There we go. Okay. So we want, if we found the area of that, and then we summed up all of them, then we'd have this area, right? So if we found the area of the typical strip, and we sum up all possible typical strips, then we'd have the area of the region. So what is the area of a typical strip? Our strips are rectangles, right? So base times height. So what is the base? The base is the width of that thing. The base is the width of that thing, and that's a little change in what? X. Okay, now the height now is from here to here. This is the height of that typical strip. So is that a, so it's going to be, that's going to be a difference of two values. It's going to be a difference of y values or of x values? Yeah, so if this was like y2 up here, and this was, if this was y2, and this was down here was y1, then that height would be, how would we phrase that height? Y2 minus y1 would be the height of our strip, right? But if it's delta x, then we need to get everything in that area formula in terms of x. So we need y2 in terms of x and y1 in terms of x. So what is y2 in terms of x? I'm just going to change the order here. So y2 is defined by our line. So y2 equals, this is y2 right here. This is y2. 6 minus x. Okay, and what is y1? Y1 is defined by our cubic curve there. So minus 1/2 x cubed. So that's our setup work. We can put a box on it, put a box around it. So our area of our typical strip is 6 minus x minus 1/2 x cubed, all times delta x. Area of a rectangle. Area of a rectangle. Okay, and so then this area then is going to be, total area will be, we're going to sum up all the typical strips. So there, it's delta x, so it's going to be, there's going to be the leftmost strip all the way to the rightmost. So the leftmost strip is at what x value? 0, because it's the y-axis, right? So imagine that red strip, the very first one is over here at the left. So the first one is at x equals 0. And the last one is all the way over here at something we have to find. Okay? So the very last strip, you imagine, is right at this x value. It's like, becomes like a point where it gets crunched between our two curves, right? That's the very last little strip. So we need that x value of the intersection. So we're going to solve this system of equations for the x that gives the same y, right? So this, you have the same y value for both, and so we want to solve for x. So it's going to be 1/2 x cubed equals 6 minus x. So we have to have a little bit of algebra here. So I can move that x over to the other side. So 1/2 x cubed plus x. Let's see here. So we would need this. So if linear or quadratic, you should be able to solve that algebraically. Okay. But so we have a cubic, so we need something else. So you could find that point with technology. Okay. Because this is not a quick and easy solve it by hand. So this would be appropriate to use your graphing calculator to solve that. Or maybe we can just kind of reason this out. What x value is going to be the same if it's 1/2 x cubed equals 6 minus x? So using technology is okay. But we can see that if you put 2 in, it's going to make it equal, right? 1/2 times 8 is the same as 6 minus 2. All right, so it's x equals 2. But if you can't see that, using technology is fine. So we're integrating from 0 to 2. Our leftmost strip is at x equals 0. Our rightmost strip is at x equals 2. So we're going to add up all the strips from 0 to 2. And what are we adding up? All the strips. 6 minus x minus 1/2 x cubed dx. Look, the dx is part of the math. We've said this before. It's not just an indicator that we're taking an integral. It's just not, that's that thing that we put at the end when we take an integral. No, it's part of the math. It's the width of the rectangle, delta x. You need it. It's part of the math because we're summing up the areas of rectangles. That whole thing is the area. Questions on this? Another easy antiderivative and solve. Okay? Anybody have a question? Okay. Next one. Area enclosed by x equals 1 minus y squared and x equals 2y squared. Okay, so you have to have some way, some method for being able to sketch these x in terms of y graphs. So what we're used to is y in terms of x, and that's how your graphing calculator is set up, to take y equals an expression of x and graph it for you. You've got to have some way to make sense of x equals, to be able to graph things like this. So let me show you one way to do that. One way to do that would be, if you know what y equals 1 minus x squared is, and you know what y equals 2x squared, so switch them back to what you're used to. If you can sketch those, then it's just going to be flipped on your axes, right? So these will just be flipped on your axes. Y equals 1 minus x squared opens up or down? Opens down with a vertex at 1. So what does it do? It opens on the negative y-axis, starting from y equals 1. So now what will x equals 1 minus y squared do? It will open on which axis will it open up on? If y equals 1 minus x squared opens up on the negative y-axis, then what about x equals 1 minus y squared? It'll open up on negative x-axis and have a vertex at not y equals 1, but x equals 1. So let's put 1 right there. So it's going to be like this. So I just sketched x equals 1 minus y squared. If you solve for y in that equation and put it in your graphing calculator, you will not get that curve. because when you solve for y, you get a square root. It's actually you'd have to use two y functions to get this. Okay, so that's what. So you have to have some way of getting the entire curve x equals 1 minus y squared in these situations where you have x in terms of y. Okay, what about x equals 2y squared? So y equals 2x squared is just, it's going to be our basic parabola stretched up times 2, right? Stretched up times 2. All the y values are 2 times what they were before. So that opens up on what? Y equals 2x squared opens up on positive y. So x equals 2y squared is going to open up on positive x. And it's going to be stretched times 2. So here is our x equals 1 minus y squared. So I'm telling you that when x is in terms of y for these curves, it trips students up, especially if you're depending on your graphing calculator. Because if you solve for y and you only take the positive version, you don't get the whole curve, right? So if you solve for y and just take the positive square root, you're just going to get half of it. So you have to have a way, somehow you have to have a method of knowing how to sketch these, okay? X in terms of y. Now I want the area enclosed by those two. Does it say anything about an axis? No. So the axes are off the table. It's not gonna. The region is not going to be formed by the x or y axis. So for instance, it won't be this because this uses the y-axis. It won't be just this here. If it was just this right here, it'd be formed by the x-axis. So it's truly the area enclosed by just those curves, not any axis. Do you see what it is? Yes, it's enclosed by both. Will be all this. I'll do it in blue. Okay, so that is the area enclosed by both. And no axes, right? No axes. Okay, so we want to look at a typical strip. So I just drew a typical strip there. Anything you notice? There's something different about this. So if I'm going to start with my typical strips here at 0, what's going to happen? So imagining all the typical strips. What happens right here? Well, you can start decreasing, but I'm going to define my typical strip by the height of this curve here, and then the bottom by this curve here. What's going to happen over here? Do you see that I have a different typical strip over there? Because it's the top and bottom of that strip is defined by different curves. So it's like I'm marching across with my typical strips. I get to the intersection point, and now my typical strip is defined by different curves. It's not defined by the same curves top and bottom the whole way across. Okay? So how can I? So if I were to take this approach, what would I have to do? What would that area calculation look like if I were to take this approach? Exactly. I would have to end my first integral here at the intersection and then start a new integral where the new curves are defining that strip. But there's some. Go ahead. Yeah, and then we'd have to know that intersection point between them. So if we take this approach, we would have two integrals. We'd have to find the intersection of x. We'd have to integrate from 0 to that intersection, with our typical strips being defined by this curve. And then we'd start at that x intersection. We'd have a new integral where our typical strips are defined by this curve. But there's a easier, a totally different approach that's much easier. So is there, yes? Right. So far all our examples have been vertical strips. We can do horizontal strip, and that's much more appropriate for this problem. Instead of doing the vertical strip, let's do horizontal strips. So I'll sketch it again. So our region is something like this. And so now what I want to do is do a horizontal strip. Sorry, this is not a point. There we go. So that's our region. I'm going to do a horizontal strip. Now, horizontal strips, we're going to add up from the bottom to the top. We're going to start, our first strip was going to be, instead of left to right, our first strip will be down here at the bottom, and then our last strip will be here up at the top. So, can we just have one typical strip all the way across from bottom to top? Is it the same definition of the left side of the strip and the right side of the strip all the way from the bottom to the top? Yeah. It's always this curve on the left the whole way up, and this one on the right. Okay, so we're ready to go. We want the area of a strip is going to be base times height. Again, it's a little rectangle. What's my base? Now, so you could, what makes sense to be the base? So width times height, I guess width times height. So delta y now, right? So I'm turning it on its side. I'm calling the base the skinny side. Base is the skinny side. Height is now horizontal. Okay, height is horizontal. So how do we define that height? Height is now what? Looking from here to here. So what is that distance across, which I'm calling the height of this rectangle? y2 minus y1? Aren't these x values? They're going to be x now. It's going to be x2 minus x1. But if it's delta y, I got to write x in terms of y. But that's exactly what we were given, right? What's x2? So x2 is the rightmost, right? The rightmost curve. Which one is that? The 1 minus y squared. This is our 1 minus y squared curve over here. And our x1 is defined by this curve here, the leftmost, 2y squared. And so now we've got it. Set up work in a box. And now we're going to sum up we're going to sum up all these strips, 1 minus y squared minus 2y squared. Okay, from what to what? The first strip is at the lowest y value down there at the bottom. So we're going to need that intersection point. And we're going to need, the last one's going to be at this. So this is going to be our y starting strip, and then our final y strip at the top. So how do we get those? Again, we're looking for y values where x is the same. So we can, again, we can set those x values equal and find the y values. So 1 minus y squared equals 2y squared. So 3y squared equals 1. Y equals the square, plus or minus the square root of 1/3. So those intersect at y equals negative radical 1/3, positive radical 1/3. So that's going to be where our first lowest strip there is, at negative 1 over radical 3. Up to 1 over radical 3. So this is area total equals all summing up all the typical strips, starting at y equals negative 1 over radical 3, all the way up to the last one, positive 1 over radical 3. And remember the dy, it's part of the math. This whole thing is the area of our strip. Dy being the dimension, the up and down, this really small up and down dimension of that strip. Okay, questions on this one?